Something is awry in our understanding of the universe. Cosmology seems to be heading for a showdown on one of its most basic questions: how fast is the universe expanding? For more than a decade, two types of measurement have been in disagreement. Observations of the current universe typically find the rate of expansion, called the Hubble constant, to be about 9% faster than predictions based on early universe data. Researchers hope that James Webb, the most advanced telescope ever built, would help settle the question once and for all. But consensus has so far failed to materialize. Instead, the Supreme Observatory has cemented the discrepancy with stunningly precise new observations that threaten to upend the standard model of cosmology. The new physics needed to modify or even replace the 40-year-old theory is now a topic of debate. An exciting and interesting possibility is that there's something we don't understand about the universe. Join us as we dig deep into how new ultra-deep images from James Webb just confirmed there is something seriously wrong with our understanding of the universe. Our universe started with a bang, the Big Bang. Energy, mass, and space flashed into existence all within a fleeting instant. Then, the young cosmos was formed, an expanding, roiling plasma broth of matter and antimatter particles that popped into existence only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma mirror should have consumed each other entirely. But scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high energy density of the early universe's crowded contents stretched spacetime, pulling a small fraction of this matter safely from the fray as the universe inflated like a balloon. The standard story goes, ordinary matter, which interacts with light, congealed around clumps of invisible dark matter to create the first galaxies connected together by a vast cosmic web. Initially, as the universe's content spread out, its energy density and therefore its expansion rate decreased. But then, roughly 5 billion years ago, galaxies began to recede once more at an ever faster rate. The cause was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our cosmos grew, its overall matter density dropped while the dark energy density remained the same, gradually making the latter the biggest contributor to its overall expansion. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda cold dark matter, or LCDM, model of cosmology, which maps the growth of the cosmos and predicts its end, with matter eventually spread so thin it experiences a heat death called the Big Freeze. Many of the model's predictions have been proven to be highly accurate. But here's where the problems begin. Despite much searching, astronomers have no clue what dark matter or dark energy are. As Ofer Lahav, a professor of astronomy at University College London who is involved in galaxy surveys of dark energy, said, most people agree that the universe's present composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing fact is we don't understand the last two of them. But an even greater threat to the LCDM model has materialized. Depending on what method astrophysicists use, the universe appears to be growing at different rates, a disparity known as the Hubble tension. Methods that peer into the early universe show it expanding significantly faster than LCDM predicts. Those methods have been vetted and verified by countless observations. Therefore, as Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb measurements, said, the only reason that I can understand at this point for them to disagree is that the model that we have between them is perhaps missing something. Measuring the universe's expansion takes a little bit more than a radar gun. The first method to measure this growth looks at the so-called cosmic microwave background, or CMB, a relic of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump as the universe exploded outward. This soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter and a value for the cosmological constant or dark energy. Plugging these into the standard model spat out a Hubble constant of roughly 67 km per second per megaparsec. A megaparsec is 3.26 million light-years. Let's pause on this number for a moment. If a galaxy is at a distance of 1 megaparsec away from us, that means it will retreat from us and us from it at 67 km per second. At 20 megaparsecs, this recession grows to 1,340 km per second and continues to grow exponentially from there onward. If a galaxy is any further than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables, dying stars with helium gas outer layers that grow and shrink as they absorb and release the star's radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt found that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness and therefore gauge its distance. It was a landmark discovery that transformed Cepheids into abundant standard candles to measure the universe's immense scale. By stringing observations of pulsating Cepheids together, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. It's one of the most accurate means that astronomers have today for measuring distances. Wendy Friedman, an astrophysicist at the University of Chicago, said, "To build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. The next rungs are added using Cepheid readings alone. Then, astronomers look at the distances of the stars and supernovas on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant." In 2019, the method was used by Rees and his collaborators, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive, an impossibly high expansion rate of 74 km per second per megaparsec when compared to the Planck measurement. However, Hubble lacked the necessary precision for the crowded regions of space the team was studying, causing some distant Cepheids to blur into neighboring stars. Dissenting cosmologists had some room left to argue that the result, however shocking, could have come from a measurement error. So when James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it. At 6.5 meters wide, Webb's mirror is almost 3 times the size of Hubble's, which is just 2.4 meters wide. Not only can James Webb detect objects 100 times fainter than Hubble can, but it is also far more sensitive in the infrared spectrum, enabling it to see in a broader range of wavelengths. By comparing Cepheids measured by James Webb in the galaxy NGC 4258 with bright Type Ia supernovas, another standard candle because they all burst at the same absolute luminosity in remote galaxies, Rees and his colleagues arrived at a nearly identical result, 73 km per second per megaparsec. Other measurements, including one made by Friedman with the Hubble Space Telescope on the rapid brightening of the most luminous tip of the branch red giant stars and another with light bent by the gravity of massive galaxies, came back with respective results of 69.6 and 66.6 km per second per megaparsec. A separate result using the bending of light also gave a value of 73 km per second per megaparsec. Cosmologists were left reeling. According to Ryan Keeley, a cosmologist at the University of California, Merced, who has been working to explain the Hubble tension, the CMB temperature is measured at the level of 1% precision, and the Cepheid distance ladder measurement is getting close to 1%, so a difference of 7 kilometers per second, even though it's not very much, is very, very unlikely to be a random chance. There is something definite to explain. The new result leaves the answer wide open, splitting cosmologists into factions chasing staggeringly different solutions. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 conference at the Kavli Institute for Theoretical Physics, KITP, in California only caused more frustration. As David Gross, former director of the KITP and a Nobel laureate, said at the conference, we wouldn't call it a tension or problem but rather a crisis. But how things can be fixed is unclear. Rees is pursuing a tweak to the LCDM model that assumes dark energy isn't constant but instead evolves across the life of the cosmos according to unknown physics. However, Keeley's research contradicts this. He and his colleagues found that the expansion rates matched the predictions of the LCDM model all the way back to the CMB. So if the model needs fixing anywhere, it's most likely in the very early universe. It could be possible to add some extra dark energy before the emergence of the CMB, giving some additional oomph to the universe's expansion that needn't make it break from the standard model. Another group of astronomers is convinced that the tension, alongside the observation that the Milky Way resides inside an underdense supervoid, means that LCDM and dark matter must be thrown out altogether. What should replace it, according to Pavel Kropa, a professor of astrophysics at the University of Bonn, is a theory called modified Newtonian dynamics, MOND. The theory proposes that for gravitational pulls 10 trillion times smaller than those felt on Earth's surface, such as the tugs felt between distant galaxies, Newton's laws break down and must be replaced by other equations. Other astronomers say that their own calculations nix the MOND claims. Yet Kropa insists that cosmologists looking to tweak the standard cosmological model are basically adding additional complications to an already very messy and complicated theory. According to Kropa, what we are experiencing and witnessing is an essential breakdown of science. A more optimistic thought is that the standard model just needs a tweak. Or maybe dark matter and dark energy are the modern-day equivalent of epicycles, the small circles ancient Greek astronomers used to model planets orbiting Earth. The orbits of planets were described very accurately by epicycles, Lahav said. It was a good model, but once astronomers placed the Sun in the center of the solar system in newer models, epicycles eventually became irrelevant. If we want to go philosophical, maybe that's what's going on. But maybe also there is dark matter and dark energy, and it's just not been discovered yet. Cosmologists are looking for answers in a number of places. CMB experiments, such as the CMB-S4 project at the South Pole and the Simons Observatory in Chile, are searching for clues in ultra-precise measurements of the early universe's radiation. Others will look to the dark matter maps produced by the European Space Agency's Euclid Space Telescope or to the Future Dark Energy Survey conducted by the Dark Energy Spectroscopic Instrument. Although it now may seem less likely, it's also still possible the Hubble tension could be resolved by figuring out some unseen systematic flaw hiding inside current measurements. And for scientists like Friedman, such a solution, or possibly further riddles, will come from James Webb. Her team is using the telescope's powerful eye to make ultra-detailed measurements of Cepheid variables, tip of the red giant branch stars, and a type of carbon star called JWST stars, all at once. Once the necessary data is collected, we'll see how well they agree, and that will give us a sense of an overall systematic answer, she said. In other words, one day the James Webb Telescope could settle a long-standing debate. Just hope that day comes soon. After all, as you see, while it would seem that scientists and astronomers know an awful lot about the universe, there are yawning gaps in our understanding of the universe and the laws that govern it. These are the mysteries that will be troubling physicists and astronomers over the next decade and beyond. Here are 6 biggest mysteries that will be troubling physicists and astronomers over the next decade and beyond. 1. why is there something rather than nothing? In the beginning, according to the standard picture of cosmology, was the inflationary vacuum. It had a super high energy density and repulsive gravity, causing it to expand. The more of it there was, the greater the repulsion and the faster it expanded. In common with all things quantum, this vacuum was unpredictable. At random locations, it decayed into ordinary, everyday vacuum. The tremendous energy of the inflationary vacuum had to go somewhere, and it went into creating matter and heating it to a blisteringly high temperature, into creating Big Bangs. Our universe is merely one such Big Bang bubble in the ever-expanding inflationary vacuum. Remarkably, this whole process could have started with a piece of inflationary vacuum with a mass equivalent to a bag of sugar. And conveniently, the laws of physics, specifically quantum physics, permit such matter to pop into existence from nothing. Of course, the next obvious question now is, where did the laws of physics come from? In 1918, German mathematician Emmy Noether shed light on this. She found that the great conservation laws are mere consequences of deep symmetries of space and time, things that stay the same if our viewpoint changes. A striking property of such symmetries is that they are also symmetries of the void, of an entirely empty universe. So maybe the transition from nothing to something was not such a big deal. Maybe it was simply a change from nothing to the structured nothing of our galaxy-filled universe. But why did the change happen? The American physicist Victor Stinger pointed to the fact that as the temperature drops, water turns into structured water or ice because ice is more stable. Could it be, he speculated, that the universe went from nothing to structured nothing because structured nothing is more stable? 2. Why is there a monster black hole in the heart of every galaxy? There are about 2 trillion galaxies in our universe, and as far as we know, almost everyone contains a central supermassive black hole. They range in size from monsters weighing almost 50 billion times the mass of the Sun to the 4.3 million solar mass Titan known as Sagittarius A** in the core of our Milky Way. But how they got there is one of the great unsolved mysteries of cosmology. We know that a stellar black hole forms in a supernova explosion in which the core of a star implodes, but nobody knows how a supermassive black hole forms. For most of cosmic history, the centers of galaxies have been where a lot of matter is confined in a small volume. It could be the case that supermassive black holes form in a dense star cluster out of stellar black holes which repeatedly merge with each other. Tentative evidence for this comes from a merger between 2 black holes revealed by a detection of gravitational waves. One hole was too big to be a supernova relic and so may have originated in an earlier merger. An alternative way to form a supermassive black hole is from the direct shrinkage of a dense cloud of gas. It could be that they form from a combination of cloud collapse and black hole mergers. It is also possible that supermassive black holes formed in the Big Bang. This would provide a novel answer to the cosmic chicken and egg question, which came first, galaxies or supermassive black holes? Rather than galaxies forming first and then spawning such monsters, supermassive black holes would form first and provide the seeds about which galaxies of stars formed. Despite their masses, even the biggest supermassive black holes are hardly bigger than the solar system, but they project their power across millions of light-years by means of oppositely directed superfast jets of matter. Where such jets are fast in the inner regions of a galaxy, they drive away gas and snuff out star formation. Where they have slowed in the outer regions, they compress gas and trigger star formation. In fact, powerful jets from the biggest holes seem to control the masses of stars that form, with a tendency towards smaller, cooler stars like our Sun. So who knows, it might be the case that we can thank Sagittarius A** for our Sun, without which you probably wouldn't be reading this page. 3. What is dark matter? Dark matter gives out no light or too little light for us to detect. We know it exists because we see the effect of its gravity on the visible stars and galaxies. For instance, the Milky Way could not have dragged in enough matter to make its stars in the 13.82 billion years since the Big Bang without there being a lot of invisible matter whose extra gravity speeded things up. The European Space Agency's Planck satellite found that dark matter accounts for 26.8% of the mass energy of the universe compared with the 4.5% of normal atomic matter. It therefore outweighs the visible stars and galaxies by a factor of about 6. For a long time, the favored candidates for dark matter particles have been weakly interacting massive particles, WIMPs, but although these particles fit the bill, they have failed to appear at the Large Hadron Collider near Geneva in Switzerland. A candidate gaining favor is the superlight axion, a hypothetical subatomic particle. A rank outsider remains primordial black holes left over from the Big Bang. Puzzlingly, no Earth-based experiment has found any evidence of dark matter despite decades of searching. It is conceivable that it is not our theory of matter that needs modification but our theory of gravity, or that dark matter is not a fluid made of a single particle but is complex like the atomic matter we see around us. Maybe the universe is filled with dark stars and dark planets and dark life. 4. Does time exist? Time is what stops everything happening at once, said American physicist John Wheeler. But time is a slippery concept. Most of what we think we know is false. For instance, we imagine time flowing. However, for something to flow, it must flow with respect to something else. Just as a river flows with respect to a riverbank, so does time flow with respect to something else, a second type of time. The idea seems nonsensical. Most likely, the flow of time is an illusion created by our brains to organize the information constantly flooding in through our senses. We also have a strong sense of a shared past, present, and future. However, the idea of a common present appears nowhere in our fundamental description of reality, relativity. Precisely how someone else's time is sliced up depends on how fast they are moving relative to you or the strength of the gravity they are experiencing. These effects are noticeable only at relative speeds close to that of light or in ultra-strong gravity, which is why they are not obvious in the everyday world. Nevertheless, they lead to the idea that one person's interval of time is not the same as another person's, and that one person's interval of space is not the same as another's. Actually, it is worse. Space and time are inextricably intertwined in our universe. All events from the Big Bang to the death of the universe are laid out in a pre-existing four-dimensional spacetime map. Nothing actually moves through time. As Einstein wrote after the death of his friend Michel Besso, now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. If the expansion of the universe is imagined running backward like a movie in reverse, in its earliest moments space and time are both ripped apart. Physicists therefore suspect that in the Big Bang, time emerged from something more fundamental. As yet, no one knows what that might be. 5. What is dark energy? It's invisible, fills all of space, and its repulsive gravity is speeding up the expansion of the universe. Dark energy was discovered by astrophysicists in 1998. They were studying Type 1a supernovae, stellar explosions believed to unleash a fixed amount of energy and burn with a standard luminosity, like a cosmic 100W light bulb. The problem was that the most distant supernovae were fainter than expected. Cosmic expansion had speeded up, pushing them further away. At the time, the only force thought to be operating in the large-scale universe was gravity, which acts like an invisible web between the galaxies, breaking cosmic expansion. The discovery that the expansion of space was speeding up gobsmacked cosmologists, who were forced to postulate the existence of a substance that accounts for an astonishing 2/3 of the mass energy of the universe. This dark energy overwhelmed gravity and gained control of the universe about 5 billion years ago. One possibility is that dark energy is a cosmological constant, an intrinsic repulsion of space. Such repulsion might arise from quantum energy fluctuations in the vacuum. However, when quantum theory, our best theory of the submicroscopic world, is applied to the vacuum, theorists predict an energy density that is 10 followed by 120 zeros bigger than that of the dark energy, the biggest discrepancy between a prediction and an observation in the history of science. Conceivably, the discrepancy will disappear when we finally manage to combine quantum theory with Einstein's theory of gravity. Meanwhile, space experiments may help. One of which is dark matter hunter Euclid, which launched into space in 2023. According to scientists, this telescope is designed to measure how dark energy varies with cosmic time, hopefully providing a vital clue to solving what is the biggest puzzle in science. 6. Why have we seen no sign of aliens? In 1950, Enrico Fermi, the man who built the first nuclear reactor, was having lunch in the canteen of the Los Alamos bomb lab in New Mexico when he suddenly said, "Where is everybody?" Everyone around the table knew exactly what he meant. Decades later, Fermi's question was examined independently by the American physicists Michael Hart and Frank Tipler. Hart considered aliens spreading throughout our Milky Way, and Tipler considered self-replicating machines that, on arrival at a planetary system, exploit the resources to build two copies of themselves that continue voyaging. Both concluded that even at modest speeds of travel, every star in the galaxy would be visited in a fraction of the age of the Milky Way. As Fermi realized, the aliens should be here on Earth. They do not appear to be. This became the Fermi paradox. Hundreds of explanations have been proposed, but consensus has so far failed to materialize. Thus, it remains a puzzle. But that's understandable. As Douglas Adams observed so perceptively in The Hitchhiker's Guide to the Galaxy, space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.